Okay, let's do a few examples on classifying discontinuities. So let's take a look at this function here. We see that when x, so to determine graphically if we have a discontinuity, we just start tracing along the graph, and if we have to pick up the pencil to continue, that means we have a discontinuity there. So we see that we have to pick up our pencil at x equals -1. We also have to pick up the pencil at x equals 1. So those are both discontinuities. So we'll classify the one at x equals -1. So at x equals -1, we see that if we just fill in that dot right there, then in order to trace the graph, we would no longer have to lift our pencil. That means that discontinuity at x equals -1 is removable. Okay, at x equals 1, we see that to the left of x equals 1, the function values are going down to -infinity. It also turns out that they're going to +infinity on the right, but we just need one of them to happen. And when that happens, we have an infinite discontinuity. Okay, so we have an infinite discontinuity at x equals 1. Okay, let's move to the graph B here. If we traverse the graph with our pencil, we never have to lift it to continue. So this function here has no discontinuities. It's a continuous function. All right, graph C here. If we trace along here, we see that we have to jump up here in order to continue the graph. Okay, so it's not just sufficient that you jump up for just one point. It's a jump discontinuity if you're going along and then jump up, and from there you don't have to lift your pencil. Okay, so at x equals 2 here, we have a jump discontinuity. Also, we know it's not a removable discontinuity because sometimes people confuse a jump with a removable. A removable discontinuity means we could fill in that missing piece and get a continuous function. The only way to fill in the missing piece here, so that we wouldn't have to lift our pencil, is with a vertical segment. But now it's not going to be a function anymore. Okay, so that means that this here is not a removable discontinuity. We have a jump discontinuity at x equals 2. Okay, let's look at the last one here. So we trace along, no problem, then boom, all of a sudden at x equals 2, we have to jump up there because that's f of 2 is equal to whatever that y value is. So we go along, there we have to lift our pencil, so we know we have a discontinuity at x equals 2, but then from there we get to just keep going. Since we can redefine our function here, so instead of having this be the y value, we could put it right there, and then as a result, we would no longer have to lift our pencil. Since that happens, that means that's going to be a removable discontinuity at x equals 2. Okay, again, we redefine the function by filling in that dot, then it's continuous after that, so that means it's going to be a removable discontinuity. Okay, so that's how you can tell graphically if you have a discontinuity. Let's see some where we have a symbolic function. Okay, let's take a look at this first one first. F of x equals x cubed plus 4x. That right there is a polynomial, and polynomial functions are continuous on all real numbers. Okay, so since polynomials are continuous everywhere, this function here has no discontinuities. Okay, let's move on to the second one. This is a rational function, and the discontinuities of a rational function are all the values of x that make the denominator 0. Then the big question is, which of those x values is going to correspond to a hole in the graph, or a movable discontinuity, and which of those x values is going to correspond to a vertical asymptote, or an infinite discontinuity? To answer that question, we need to factor the numerator and the denominator. Okay, so the numerator factors as x plus 2 times x minus 2. The denominator factors as x plus 2 times x plus 3. we notice that the x plus 2's will cancel out. That leaves us with an x plus 3 in the denominator. And so what that means is that we have a vertical asymptote. So you remember from finding vertical asymptotes, the way we figure out where we have a vertical asymptote is we simplify, and then whatever still makes the denominator 0, that's where we have a vertical asymptote. So at x equals -3, we have a vertical asymptote or an infinite discontinuity. At the value of x coming from the term that canceled with the numerator, okay, the function is undefined there, and what's happening on the graph is we have a hole. So at x equals -2, which is what makes this equal to 0, at x equals -2, we have a hole in the graph, which is also called a removable discontinuity. Okay, so those are the two types of functions that you should worry about finding discontinuities on without a graphing calculator. Okay, so again, polynomials are continuous everywhere. Rational functions, the discontinuities are whatever value of x makes the denominator 0. So in this case, -3 makes it 0, and -2 makes it 0. If you can cancel out the term that yields one of them, then it becomes a removable discontinuity. Whatever term still remains, that yields an infinite discontinuity.